So, and I gave you this assignment. So, what is enthalpy change of combustion of C2H3S? That is when one mole, it's the energy change that is associated when you have 1 mole of C2H3S and it burns in oxygen, excess oxygen, it completely burns and produces whatever it's going to produce. The carbon would get converted into carbon dioxide. The hydrogen would get converted into H2O, and I told you that sulfur would be turned into sulfur dioxide. So this is what the combustion reaction would be, and you need to balance it. So there's going to be 2 carbons, and there's going to be how many hydrogens? There's supposed to be 3 hydrogens, so I would have to multiply this by 3 divided by 2, 1.5. And there's only 1 sulfur, so that's fine. And then I need to count the oxygen. So over here I have 4 oxygens. Over here I have 1 point. So oxygen is kind of hard to balance. It's 4 over here, 1.5 oxygens over here. So that's 5.5 plus 2 more. So that's 7.5. So that's 7.5. So O2 over here would be 7.5 divided by 2. So that's kind of or 15 divided by 4. So, I mean, this one came out to be in a lot of
3.7.
fractions. 3.75 because you had to keep this 1 mole. When you talk about enthalpy change of combustion, this has to be kept as 1 mole, which is why everything else had to be in fractions then. Okay, is this clear?
Yes.
Yes, sir.
Let's just quickly do enthalpy of formation of H2SO4, and that's going to be that 1 mole of H2SO4 is formed from its elements, which are hydrogen, sulfur, and the elements must be in their standard state. So 1 mole of a substance is formed. So here's it getting formed. So there's going to be 2O2, there's going to be just 1H2. So this is gas. You have to write the states as well. So this one is now H2SO4. If it's not dissolved in water, it's a gas as well. But it can be aqueous as well. So it depends on the question. So I think I should have been more specific about this, whether H2SO4 is a gas or a or in aqueous state. Okay, let's assume it's in gaseous state. Now, moving on, other definitions. So let's talk about standard enthalpy change of atomization. So standard enthalpy change of atomization. And it's often referred to as the symbol is ΔH. There's going to be AT written or ATOM written. The knot is there just to tell you that everything is measured under standard conditions. So that's your enthalpy change of atomization. So what happens in that? In this, it's first thing, it's always endothermic. It's always going to be endothermic. Why? Because it's the energy that would be absorbed when 1 mole of gaseous atoms are formed. So it's the energy that is absorbed when 1 mole of gaseous atoms are formed from its constituent. From what? From its constituent element in its standard state. And obviously measured under standard under standard, measured under standard conditions. So I'll just write. So this is the definition of what enthalpy change of atomization is. So what that basically means is that it's energy absorbed when you're forming 1 mole of gaseous atoms of any substance. So for example, so this is what you're trying to form: 1 mole of gaseous atoms. So let's say I'm making 1 mole of gaseous atoms of carbon. And from what? Formed from its constituent element. What's the element? The element is also carbon. But the element must be in its standard state. So carbon is in solid state at room temperature. Carbon is either graphite or it's diamond. Usually when we refer to carbon, we're talking about graphite, right? So I mean the structure of graphite. So usually when we talk about carbon, it could be in the form of diamond. It could also be in the form of graphite. So we've been normally talking about it in terms of graphite. So this is uh, so this over here is our graphite. And why is it always endothermic? Because if I want to make gaseous carbon atoms, then I would have to break all of these bonds. I mean, this bond has to go, this bond has to go, all the carbon-carbon bonds, they have to be broken. Only then can I get 1 mole of gaseous carbon atoms. So all the carbon atoms would fly around and I'll get 1 mole of gaseous carbon atoms. So is this clear?
Yes.
Yes.
Achha, so whenever you try to make 1 mole of gaseous atoms of anything from its element, that would be the energy change that is associated with that is going to be called the enthalpy change of atomization of that particular element, like carbon over here in this case. Now the element must be in its standard state. So for example, if I want to make 1 mole of oxygen, so 1 mole of oxygen gaseous atoms, just 1 mole. If I want to make those, then I would have to make it from its element, and the element must be in its standard state at room temperature. So oxygen is in the form of O2 gas. So since this has to be kept as 1 mole, I would have to multiply O2 gas with half just to balance this equation. So this would be referred to as the enthalpy of atomization of oxygen. Like I'm forming 1 mole of gaseous oxygen atoms from its element. Uh, yes, Abdullah.
So, sir, basically, we are converting constituent elements to their like monoatomic form.
Yes, exactly.
Okay. Right. Okay. Understood.
See. So you're breaking all the atoms, which is why it's endothermic. As I so for example, bromine. I want to form 1 mole of bromine gaseous atoms from its element. The element is, now you must know what the elemental form is. Bromine is a diatomic molecule and it is a liquid. Remember, all group 7 elements are diatomic, and this would be multiplied by half as well. If I want to do this for iodine, 1 mole of iodine gaseous atoms would be formed from its constituent element. Now, the elemental form of iodine is I2 at room temperature, and it is a solid at room temperature, and this would be multiplied by half as well. So just remember, you're just trying to make 1 mole of gaseous atoms from its element. Uh, why is it endo? Because only bond breaking is happening. So the explanation for it being endo is, I mean, you're not forming any bonds, you're just breaking bonds, only bond breaking taking place. Yes, Abdullah.
Sir, isn't iodine supposed to be liquid because it's a group 7 element?
Remember group 7 elements one by one. Just go through them. Uh, so you've got fluorine gas, which is a very pale colorless yellow gas. I mean, it's kind of colorless. So this is fluorine. Okay.
Okay.
Uh, you've got chlorine at room temperature. That's also a gas. That's a greenish yellow gas. That's much darker in.
Right.
Okay. Then you've got bromine. And remember that bromine is a liquid at room temperature.
Okay.
So here's your bromine.
Right.
And iodine is a solid. It's a blue black crystal at. I mean, this is iodine. It's a blue black crystal. I mean, it fumes. It sublimates. Like you can see the fumes forming.
Mm-hmm.
Purple fumes are formed when iodine sublimates. But it's a blue black, shiny blue black crystal, uh,
Okay.
which evaporates to form these fumes. Okay, just
Okay.
a
Sahi.
brief recap of
I
this.
understand. I understand.
So remember, in this, what you just have to remember is what are the elemental form at room temperature? What do the substances exist in? In what form do they exist? I mean, you can be asked to write the same equation for a metal, for example. Like you can be asked about writing it for just one second. Let me extend the. So is this clear to so far? Cosa, is this clear? Nabila, is this clear?
Yes.
Yes. Yes, sir.
So you could be asked about the same thing for copper as well. So here's copper. You're forming 1 mole of copper gaseous atoms, and the elemental form at room temperature, it's in the form of a solid metal. It's a pink metal. So you're just breaking. Now remember, every time you're basically breaking different types of bonds. Like over here, you're breaking metallic bonds because copper is a metal. Over here, you're trying to break covalent bonds because these molecules are covalent. So remember, the bonds that would be broken would vary from substance to substance. And if you have stronger bonds, just remember this point at the moment. Smaller atoms, they always form stronger bonds because they're close together. So the force of attraction is a lot more. So smaller atoms, they form stronger. They form stronger bonds, which are harder to break. So the enthalpy change of atomization is higher. You would need more energy to break bonds if the substance that you're talking about has small atoms. Uh, so I guess for iodine it would be kind of easy because iodine is a very big atom, so the bonds are going to be they're going to be very very weak. Now another thing about enthalpy change of atomization is that you're given your data booklet. Okay, just one second. Where's the? So you have your data booklet over here. Sometimes, just sometimes, a value of enthalpy of atomization can be found from the data booklet as well. For example, in this case, the enthalpy change of atomization can be found. It can be found using bond energies. Like if you know exactly how many bonds are being broken. For example, over here in this reaction, if you look at this reaction, you're only breaking the oxygen-oxygen double bond. So in this case, enthalpy of atomization of oxygen is basically equal to, I mean, you're breaking the oxygen-oxygen double bond. So it's going to be equal to the bond energy of oxygen-oxygen double bond, but half of them. I mean, you're just breaking half a molecule. So it's going to be equal to the to half the bond energy of the oxygen-oxygen double bond. So in the data booklet, we already did this part that there's a page where bond energies are provided. So yeah, for example, over here, the oxygen-oxygen double bond is given. That's 496. So you're just breaking half of a molecule. So 496 into half. That would kind of give you 240, what, 248. So 248 is going to be your answer. But only sometimes. I mean, is this point clear to everyone?
I
Sir,
see. I understand.
Yes, Franz.
what's the difference between enthalpy change and bond energy?
Nee, what's the difference? Nee, bond energy is the energy that's needed to break the bond. Enthalpy change is the overall energy of the reaction. Like in an overall reaction, there's bonds broken and bonds formed. Both things are happening. So bond energy is basically the energy that is required to break one very specific bond. Is this clear?
Yes, sir.
Actually, now, so remember we discussed early on. We discussed somewhere. We did this thing. Bond energies. I told you that the enthalpy change of the reaction, the overall energy change of a reaction, can be found using bond energy. But I gave you a warning that don't use bond energy if equation contains solids or liquids. Why? Because I told you that bond energies are that are given in the data booklet. They're only calculated for gaseous substances. So if in the reaction all substances are gaseous, then you can use bond energies. But if in a reaction the substances are not gaseous, for example, in this one, bromine is a liquid. Over here, iodine is a solid. Over here, copper is a solid. So in these reactions, I can't use bond energies because bond energies are only defined for gaseous molecules. So bond energy data cannot be used. So bond energy data cannot be used as substance as it is defined for gaseous substances only. So is this clear?
Yes.
Mariam, is this clear?
Yes,
Aisha?
sir.
Okay.
Yes, it's clear.
Yes, sir.
So this is enthalpy change of atomization. Just remember that you're just breaking the bonds in an element to form just gaseous atoms, and the atoms must be 1 mole. Uh, and also, that's only a few times you can actually use bond energies in the data booklet. Otherwise, uh, this value, like the enthalpy of atomization of bromine, would be given to you in the question. You can't really find it in the data booklet. Now, the next one we're going to talk about is the standard enthalpy change of. It's going to be the standard enthalpy change of neutralization. So that's the next thing, standard enthalpy change of neutralization. Now, by just looking at what it is, neutralization is an acid-base reaction, and it's always exothermic. So, whenever you have an acid-base reaction, energy is always released. So it's the energy that is released when you have 1 mole of water formed when an acid and a base So it's the energy that is released when 1 mole of water is formed when an acid and a base react, measured under standard conditions. So it's an acid-base reaction, and when you have an acid-base reaction, 1 mole of water is produced. Over here specifically, the term that is base that he's using, that's your alkenes. It's your group 1 hydroxides and some group 2 hydroxides. So an acid-base reaction happens, and 1 mole of water should be produced. So, for example, NaOH and HCl react. So, what do you get? You get NaCl and H2O. So, 1 mole of water is being produced in the reaction. So, this would be called the standard enthalpy change of neutralization. That's the symbol. It's going to be delta H, and the label would be N. So it's a neutralization reaction. So it's the energy change that is associated with a neutralization reaction. But the number of moles of water that are going to be produced, it should always be 1 mole. Is this clear?
Yes.
Yeah.
Now it could be any acid or it could be any acid or base reaction. You could have KOH reacting with H2SO4, and it could also produce salt and water. So that's going to be K2SO4 plus H2O would be produced, and you can balance it. So there's going to be 2 KOH and there's going to be 2 water molecules, right? Is this enthalpy change of neutralization or not?
I don't think so because one
No.
mole no, is not been formed. 2 moles is formed.
Okay, so over here it's not 1 mole, so you can't call it enthalpy change of neutralization. Or what you could do is you can call it the enthalpy change of neutralization, except that it's twice the enthalpy change of neutralization because because it's double the value now. Instead of forming 1 mole of water, you're forming 2 moles of water. You're forming double the quantity. So the amount of energy that would be released would also be double. So the energy change would be twice that value. Is this clear?
Yes, sir.
Yeah.
So whenever you have an acid and a base reaction, no matter what the acid or base is, a salt and a water molecule is going to be produced. Now you've got all sorts of acids. For example, you have NaOH plus ethanoic acid, which is CH3, COOH. That's also referred to as your acetic acid. So it's going to produce a salt, which is going to be this one, plus a water molecule is produced. And since 1 mole of water is produced, that's enthalpy change of neutralization. Now, the thing with standard enthalpy change of neutralization is that it always has the same value. Enthalpy change of neutralization, delta Hn, is equal to approximately minus 57. You should remember this value, kilojoules per mole. Especially for strong acids and strong bases. So the value is always fixed. So the question is, why is the value always the same? I mean, there are obviously different reactions. NaOH and HCl, that's a different reaction. KOH plus H2SO4, that's a different reaction. NaOH with ethanoic acid, that's a different reaction. So why is the enthalpy change always coming out to be the same value? Why is the energy change exactly the same? And the reason for that is because no matter what the acid or what the base is, the reaction is kind of always the same. The acid, what does it do? It produces the H plus O ion. What does the base do? It produces the OH minus O ion. The two react together to form water molecules. So at the end of the day, no matter what the acid is and no matter what the base is, it's always the same reaction happening. So the acid produces H plus O ions. So whether the H plus O ions come from HCl or H2SO4 or ethanoic acid doesn't really matter. What does the base do? The base produces these OH ions. So whether the OH ions they come from NaOH or KOH doesn't really matter. So at the end of the day, this produces OH ions, this produces H plus ions. The H and the OH ions they get together to produce 1 mole of water. So it's always the same reaction. So always the same reaction happens, which is why the value of energy change is exactly always the same. Is this clear?
Yes.
Yes.
And that's referred to as your ionic reaction, your ionic equation. So it's always the same reaction that's taking place. The other important point about this is that the value of delta Hn is slightly less exothermic. So it's kind of less exothermic than minus 57. Like it could be minus 52 or 53 for weak acids and weak bases. I said, so why is the value slightly, I mean, it's still close to minus 57, but the delta Hn value would be less exothermic than minus 57 for weak acids and weak bases. For example, this, I said, which ones are weak acids? Weak acids are your organic acids, like ethanoic acid. That's, I mean, anything that contains carbon, that's an organic acid. Like carboxylic acids that contain carbon. And bases are that have N in them. Like it could be ammonia. That's a weak base. So remember this: any compound that contains N in it, that's a weak base, and any compound that is organic acids, that's a weak acid. So why is the value less than minus 57? The reason it's less than minus 57 is because when you have a weak acid, uh, the ions are not produced that readily. Like HCl is a very strong acid. So HCl by default would dissociate itself. I mean, no energy would be required. I mean, even before the reaction, the HCl would be dissociated and would give off H plus ion. It's a strong acid. Strong acids, they ionize fully. But on the other hand, you have ethanoic acid. So when the reaction starts, the ethanoic acid would not be producing H plus ions because it's a very weak acid. It's a terrible acid. So some energy is consumed in producing these H plus ions. So you would have to sort of break the bond of H, and the same is true for weak bases as well. You would have to break the OH bond because they don't ionize fully. So some energy. So why is it less exothermic? Why does it produce less energy? Because some energy gets used up. So some energy gets used up in ionizing the weak acid or base. So the thing is, for strong acids, you don't have to produce H plus ions because the H plus ions would already be there. The HCl molecule would already be ionized. But for weak acids, some energy has to be spent because it's not going to produce H plus 1 that readily. So some energy would be wasted in breaking the H plus 1 ions. Is this idea clear?
Yes.
Yes.
TK, everyone, is this clear? So,
Yeah.
acha. So just remember, enthalpy change of neutralization, it's always the same value, minus 57. At least for strong acids and strong bases. Why is it the same value? Because it's always the same reaction. I mean, the rest of the ions are kind of spectator ions, whether it's NaOH or whether it's KOH. The Na and K, they don't really have a role. It's just the OH ions reacting with the H plus 1 that are coming from the acid. So the other ions are just spectator ions. They're not doing much, which is why the reaction is always the same. And for weak acids, I told you that the value would kind of get slightly less exothermic. Now, the next one that we are going to do is the next definition that we're going to do is it's enthalpy change of which one do we do? Of solution. So let's just hold on one second. So I'm going to do enthalpy, standard enthalpy change of. Now this one is simple, kind of simple. It's delta H solution. The idea is simple. You have 1 mole of a substance like NaCl. You just dissolve it in water, and it dissolves. It ends up forming ionic compounds that dissociate when they dissolve. Like the ions get mixed with water, so the ions become separated when you stir them vigorously with water. So you've got NaCl. I mean, this is what happens when you have an ionic compound, ionic lattice of NaCl. So the ionic lattice of NaCl is uh, where's the lattice? Where's the lattice? Just a second. So this one, let's pick this one. So the ionic lattice is that positive and negative ions are strongly attracted to each other. So when you stir them in water, all the ions they dissociate, they scatter, they mix with water molecules. Uh, and this is what NaCl aqueous would kind of look like. Yep, this one. This one is a good image. But let's pick this one. So this is kind of what happens when you mix it in water. Like originally, the positive and negative ions are all attached together, but when you uh, stir them vigorously with water, the ions kind of split. The positive and negative ions they go there, different paths. I mean, this is the negative ion that's traveling over here. You've got a positive ion that's going in this direction. I mean, you imagine you vigorously stirring it, and they get completely surrounded by water molecules. So all these H2O molecules they come in, and the ions would no longer be able to get back together again. So this is what happens, and this is what is meant by dissociation. Is this clear?
Yeah.
Yes.
So, which is why it's better to actually write, if you have an ionic compound, it's better to write the ions splitting up, right? Or you can simply put them together, NaCl, you can call it NaCl aqueous as well. Acha, but so what is enthalpy change of solution? Enthalpy change of solution is you take 1 mole of any substance. For example, in this case, you take 1 mole of NaCl. and you just mix it in water. And whatever the energy changes, that would be referred to as the enthalpy change of solution for NaCl. Whether it's endothermic or it's exothermic, it's going to vary. It could be endo, but at the same time, it could also be exo, depending on what type of substance you are trying to dissolve. So it could be both. Uh, and it could be any substance, not just ionic. Like if I have alcohol, ethanol, and I mix it in water, so I get ethanol again. Now that's a covalent molecule. That's not going to dissociate, but so I'm going to get ethanol again in aqueous state now. So that's another one, standard enthalpy change of solution. This would be called the ΔH solution of ethanol. So remember, enthalpy change of solution is when you just quickly write the definition. It's when you just dissolve 1 mole of any substance. So it's the energy released. It could be endo, it could be exo. So it's the energy released or absorbed when 1 mole of a substance completely mixes with water to form an infinitely dilute solution, which basically means to form a dilute solution. To form an infinitely dilute solution. So it's energy release or absorbed when you just dissolve substance. If the temperature increases, that means energy is being released. If the temperature of the solution drops, that means energy is getting absorbed, and it's going to be measured under standard conditions. Is this clear?
Sir, I have one question. We are dissolving with water, right?
When you talk about solutions, we're basically talking about water.
So why isn't there more addition of hydrogen as before the reaction?
What do you mean addition of hydrogen?
I mean, if you are mixing with water, so there must be like,
Actually,
more.
in the equation,
Yeah.
that's why you don't write water in the equation, because you're just dissolving it. You're not doing a reaction. Like you're mixing ethanol, so ethanol mixes with water, right? So,
Oh, okay.
which is why I'm just writing the state that ethanol was liquid, but now it's aqueous.
Acha, okay, I understand. Sorry.
Okay, so it's not that it's reacting with water; it's just mixing with water. Okay, this is what's happening. We just so the ions are still there, but they've just mixed with water. They're water molecules that are surrounding them now. Is this clear?
Mm-hmm. Yeah.
So, okay, let's continue with definitions. Okay, tomorrow then.
All right. Thank you.
Okay, take care, everyone.
Okay.
Thank you.
Thank you. Allah Hafiz.
Allah Hafiz. Allah.